We'll now calculate the field inside the insulator, for r less than A. We can follow the same procedure as we did for the field outside the insulator. Namely, we can apply Gauss's law using a spherical Gaussian surface centered on the origin. Since the charge is uniformly distributed throughout the insulator, we know that the magnitude of the field must have the same value at all points on the spherical surface, and the direction of the field must be perpendicular to this Gaussian surface everywhere. The only change to our calculation is that the charge enclosed by the Gaussian surface is no longer the total charge of the insulator, i.e., the integral of E dot dA is still equal to the product of the field and the cross-sectional area, but the charge enclosed by the sphere of radius r is now less than the total charge q. To calculate the field inside the insulator, we need to determine the charge enclosed by a sphere of radius r where r is less than a. Since the charge of the insulator is uniformly distributed, we can introduce the charge density of the insulator, ρ, which is defined to be equal to the insulator's total charge divided by its volume. The charge enclosed by a sphere of radius r, then, is just equal to the product of this charge density and the volume of the sphere. Consequently, we obtain the result that the electric field inside the insulator increases linearly with r. We can now plot the radial dependence of the field for all values of r as shown. Here we see that the field outside the insulator, for r greater than a, is identical to that produced by a point charge at the origin. Once we move inside the insulator, for r less than a, less charge is enclosed by our Gaussian surface, which means that the field cannot continue to increase as 1 over r squared. The exact deviation from the 1 over r squared curve depends on the exact form of the charge distribution. In this case, we assumed a uniform volume charge density, which led to the linear behavior shown. A non-uniform, but still spherically symmetric charge distribution would have led to a different radial dependence of the field inside the insulator. We'll next consider how our result would change if the insulator had been a conductor.